Hi, my name is Jacob Sindorf,
And I'm George Munn.
and this is our final project of an anatomy-inspired animatronic head. So recalling in the previous project, this is the facial expression robot. So here we have the anatomy-inspired muscles controlled by a PlayStation 3 controller. You can see each eye is able to move, look in multiple directions, as well as having a anatomically inspired and mostly correct muscle design for the face, seeing that those lips can move up and down, and even this eyes can be individually controlled as well as both sides of the lips. So to expand this project, we actually wanted to build the entire neck and shoulders to this system to add an entire head system. Here we can see that concept to expand to a neck. You have A is the previous face design, just that mask. B is the actual extension to the skull. And C would be that neck extension to allow movement to the whole entire neck and head. So starting with that is the skull extension. So just taking the dimensions of that skull mask and then adding the 3D model in SolidWorks, we were able to actually just use a soldering iron and heat that up and basically glue them together to the back of the skull as shown in that integration picture. The next step is actually this neck mechanism we found on Thingiverse. You can see this is a preliminary design of this neck moving with the PlayStation control, which we'll describe later in this presentation. However, it's a nice design that gives a lot of movement and a lot of expression to the system. And then this final one would be adding the shoulders, which we just used a laser cutter. So again, taking dimensions, we were able to cut these little notches into it and allowed to build it together with some wood glue. As you can see here, this is the final integration of all those components. We have the neck design along with the shoulders and the head. However, we realized that we needed a quick redesign of this bottom plate in order to hold the battery of the system, as it's a relatively large battery. And we also added some spacers so we can bolt in those holes at the bottom of the neck, as seen here. That allows for more easy integration of the entire system. And then that's just showing that a neck attachment in the battery. So here's a quick system test one. Again, we'll just explain the controls and everything at the end of the presentation. You can see it's a little the movement in there is a little jumpy. However, the neck adds a lot of expression to the face. And then that battery pack can sit easily behind the head. Next, we'll actually move into the anatomy inspired part of the project with the neck muscles. So starting with the deepest with 1 all the way to the most superficial muscles. On the far left, we have the deepest muscles. And in the front, we have what I called F1 for all front muscles. And then in the back, I have B1 for the back muscles. Then on 2, you can see that F2 through B3, as well as one called S1, which is the side. All of them are highlighted. Going next to the deeper or the most superficial muscles, you can see F3 and F4. We actually decided not to include B4 or the most superficial muscles as shown on that far right, as these would just cover most of the internal muscles and you wouldn't be able to see as much movement from it. So after that, we were able to design these muscles relatively in SolidWorks, then cut them in a laser cutter while aligning the stretch direction as we used that fabric that has a unidirectional stretch to it as we did with the face. And here's a quick picture of that neck muscle integration all put together with tape just to see how that design works. We were able to sew together 2 of those back muscles to allow them to work as they would intended in anatomy. And again, here's the front design and showing where they are on the system. And here's the other few front muscles that are more superficial. Here's the deepest back muscles as shown on the right there. And again, the other back muscles we used for this project. And lastly, the side muscle there on the side of the head. Now I'm going to allow George to talk about the final design and some of the electronic components of the system.
So going into final design, this is our ultimate final system that we came up with. And you can see the shoulders, the neck muscle attachments, of which we used a staple gun to attach to both the wooden base and the 3D printed plastic above. Here's the back side. You can see all of our electronics and wiring sit nicely in the back of his head. And you can see kind of in there some of the servos and the microcontroller that is hidden back underneath all those wires. So going into the electronics, so the whole circuit is fairly simple. The most complicated part of it is running all the lengthy wires from all of the different servos reliably to the microcontroller and making sure that those signals aren't corrupted. And one problem that we did discover is the interference when touching the wires actually caused some disturbance in the servos to sometimes glitch out or receive a signal that they shouldn't be receiving. But overall, you have a pin that is controlling the signal to all of the servos, and all the servos are externally powered through a 6-volt power supply. So going into software, this is just the general block diagram of kind of how the code works. You initialize everything and then you wait for the PlayStation controller to be connected. And while that is connected, it then constantly reads the controller, performs each function of which we've separated into eye control function, lip control, and the neck control, each with some fairly complicated algorithms to map the signals from the controller to actual movement of the neck or eye or lips. And then once it has a kill switch pretty much where you can press the PlayStation middle button and it will end the whole program. And there's a link to the GitHub to the microcontroller code. So going into the control, we continue to use the PlayStation 3 controller, and we simplified the controls a little bit due to the combining all of these controls into a more simple, straightforward system, therefore controlling all of the eye movement of both eyes with the right joystick, the left rotation of the neck with the left stick, and then you have your lips up and down. And then adding on some complexity is we actually use the accelerometer that gives you your gravity values in each X, Y, and Z of a coordinate system. And then we map that to the neck. So going into that, there's some complicated robotic kinematics that go into calculating what happens to an object after it experiences a roll and a pitch. So mainly from an accelerometer, you can get roll and pitch. The two equations in the top give you your roll and pitch angles from those accelerometer values. You can then use those and go into find the rotational matrices for roll, pitch, and yaw, part of robotics kinematics. You multiply these matrices together to get your overall rotational matrix. In this case, we say that yaw is 0, as yaw is a direct input and does not influence the actual positioning of the servos as it pushes up and down on the neck. So this is the overall rotation matrix. We take that rotation matrix and we multiply it by the coordinates in 3D space of the attachment points of the push and pull rods. Knowing that original attachment point, we can then take the new pitch and roll values and evaluate what occurs or where that coordinate point is, X, Y, and Z, after a rotation occurs. So what we are mostly interested in is the Z height position. So this value is identified in centimeters, and it is then needed to be correctly mapped out to degrees of the servos. And so we start our servos dead center at 90 degrees with the servo horn sticking out horizontally. And one side of the servo, it can rotate all the way up to 180 degrees for a push of 1.5 centimeters, and then all the way down to 0 for a pull of -1.5. And it is just the opposite because for the other servo, as the other servo is flipped. So using these limits, we're able to actually map the value we get from our change in height from our neck kinematics. And we were able to map that height from -1.5 centimeters to 1.5 centimeters to a degree. And therefore we can then write the degree and get the exact degree that the servo needs to be written in order to match the orientation of the object or the whole head. So going into the demonstration, this is our final demonstration video of all the components working. You can see the microcontroller in there, all the servos that control the eyes and the lips, and you can see where the staples came through to attach the muscles. In this demo, we go through each of its capabilities and what it is and how those are controlled. So you can see immediately there's immediate reaction to me picking up the controller and moving it around. And you can see with the right joystick that the eyes are moving, correlating exactly what direction you're pushing it, as if you were controlling the robot from behind its head. You have the lips, you see it pressing it, you see the lips together with the eyes, you get a nice creepy smile, a little bit of a good frown. And then here is demonstrating that full neck rotation and movement as our robot head can look up, down, and kind of roll the head around. So we actually put some dampening and proportional coefficients in the math behind it, in order to, therefore you have to exaggerate the motion of the controller in order to get the same motion from the robot. And this is out of just a safety hazard, as since the accelerometer values and Bluetooth communicate so quickly, it will react immediately to however you touch that controller. So therefore, by exaggerating those values and putting some proportional coefficients, we actually dampen its motion, and it gives us a much smoother motion for the controller. And that is our whole project. Greatly appreciate the time that we had in this class to build this project and the opportunity and guidance. And thank you very much.